SwayamPrabha. Digital India. Educated India.
Welcome to the 10th week of this course. In this week, we will look into analysis of structures which has shape memory alloy as a component. Now, for this we will refer to some research papers. However, the formulations have been done in the papers using the finite element method. So, we need to spend some time in understanding the basics of finite element method. Now, finite element method itself is a can be one course and there are lots of topics within it. Here we will look into only a small part of it which we will find relevant to understand the mathematical formulation. Now, the example structures that we will see are beam structures. So, we will see how we do finite element formulation of beam with Euler-Bernoulli approximation. So, these beams are all Euler-Bernoulli beam. While dealing with piezoelectric materials, we have looked into mathematical formulations using the energy principle or the Galerkin technique, and there all the formulations were based on Reed's method or the Galerkin method. So, there the approximation functions that we take are valid throughout the domain. So, when I solve a beam problem, if the beam has a length of L, then our approximation functions they were also valid throughout the domain from x equal to 0 to x equal to L. However, in finite element method the basic difference is that all the approximations are piecewise valid. So, the forms that we saw the virtual work equations, energy equations, they all remain same. However, when we put the approximations are piecewise approximations. So, while analyzing a beam, we saw the variational form as rho multiplied by u 0 dot minus z into del 3 by del 2 del 3 w by del 2 del t 2 del x, and then we have the variation of this term u 0 minus z into del w by del x, and the entire thing is valid throughout the domain, plus we had rho multiplied by w double dot w and then dv. So, these are the contribution from the inertia terms. So, here we are solving a time dependent problem, and then plus we have E multiplied by epsilon 0 minus z into kappa minus epsilon p, that is the free strain. So, I am just writing whatever we had for the Euler-Bernoulli beam in the piezoelectric case, and then we will drop the terms which I do not need here. So, we are quite familiar with this formulation. Now, here we are analyzing just a beam. This formulation was written based on the fact that it has some piezoelectric component in it. Now, here we do not have any piezoelectric component. So, epsilon p we do not have, and then in this case I had distributed force across x direction and across z direction, but here we are assuming that all the forces are along z direction only. So, we have P z only and P x equal to 0. So, no force along x direction, and this as we do not have any asymmetry with respect to the neutral axis. So, we do not have any coupling between the in plane and the out of plane terms. So, under a pure transverse load, I mean the load which is applied along the z direction, this beam will deflect only in the z direction. So, there will not be any u0 component induced. So, we do not have these as well, and we do not have epsilon 0, the mid plane strain as well. And apart from that, if I look into this contribution of this term, whatever is left here, the contribution of this term is also much less as compared to the contribution of the other terms, because when these two terms gets multiplied z square. So, z square on being integrated gives me I, the moment of inertia, and I is much less as compared to the cross sectional area A, and density is also much less as compared to the elastic modulus. So, this quantity is also we are going to neglect to keep the formulation simple. So, finally, we have here if I integrate this term, I will just write it once. Then we have rho I multiplied by del w double dot by del x multiplied by variation of del w by del x. So, dx, and then we have here rho a multiplied by w double dot multiplied by variation of w dx, and then our kappa is nothing but minus of z into kappa is just del 2 w by del x 2, and kappa is del 2 w by del x 2 del 2 w by del x 2. So, on being integrated I have z square, that will give me a moment of inertia, and I is multiplied. So, E I del 2 w by del x 2 into variation of del 2 w by del x 2 dx, and then minus I have P z into del w dx. So, these are all x, so equal to 0. Now, the contribution of this term is much less as compared to this term, because I is much less as compared to A, because these beams have much less thickness. So, because of the low thickness I is much less than A, and then if I compare this term with this term, although I have I in both the terms, but rho is much less than E. So, finally, we drop this term. So, after dropping this term we are only left with this. So, this is equal to rho a w double dot del w dx plus I have integral of E I del 2 w by del x 2 multiplied by variation of del 2 w by del x 2 dx minus 0 to L P z del w dx. So, we have neglected this term. So, this is our variational form that we will deal with. Now, in this form we would put our piecewise approximation and go for the finite element solution. So, to do that, our entire solution domain is x equal to 0 to L, that is the length of the beam. So, we have x equal to 0 to x equal to L, and that is our x. So, what we do is we divide the solution domain into a set of elements. Element means a set of subdomains, and then we can name each of these subdomains as some element. So, it is element number 1, element number 2, this is a generic element, element number E, and this is the last element, element number NE. So, NE is the total number of elements. Now, these points which are the two sides of the element, at the two ends of each element, they are called nodes. So, this is a node, this is a node, this is a node, and so on. So, except the first and the last node, rest of the nodes are shared between two elements. For example, this element number 1 and element number 2 shares this node, which is the second node. Now, let us look into element number E. Let us look at an enlarged view. So, we are drawing it little bigger. So, element number E, let us assume that it has a length of LE. And it has two nodes. So, this is the first node of element number E, second node of element number E, and our solution that we want is W. W is the displacement in the transverse direction. So, the value of W at the first node of the eth element, we call it W1E, and the value of W at the second node of element number E, we call it W2E. So, the superscript denotes element number and the subscript denotes the node number. Similarly, I define the slope here. So, del W by del X, the slope of W at element number node number 1 of element number E is del W by del X 1E, and this is del W by del X 2E. And these values that we are defining here at the nodes are called the degrees of freedom. So, we say this is our first degree of freedom at node element number E, this we call as the second degree of freedom at element number E, this we call as third degree of freedom at element number E, and this we call fourth degree of freedom at element number E. So, we have 2 degrees of freedom per node, and those are the value of the solution W and its slope, and so there are total 4 degrees of freedom. And also let us define a local coordinate system small x running from this node to this node. So, each element has its local coordinate denoted as small x. Now, if I put the degrees of freedom number here, so we can say we have D11 here, because this node is the first node of element number 1, and we can also say that we have D21 here, D21 here, and this we can call it D13, sorry, it is D31, this we can call D31, and this we can call D41. Similarly, this node is shared by element number 2 also. So, this displacement here, the value of W here can also be called D12, and we can call it D2 2, similarly D3 2 and D4 2. So, thus we have the nodal degrees of freedom at the nodes of each element, and because this node, the intermediate nodes are shared by 2 elements. So, I get 2 degrees of freedom here, D3 1 when I consider it for the first element, D4 1 when I consider it for the first element. Similarly, for the second element it is D1 2 and D2 2. Later on we will see that D3 1 and D1 2 are same, D4 1 2 and D2 2 are same to maintain the continuity. We will come to that later on. Now, let us again focus on a generic element E, and we have defined a local coordinate system x. Now, let us assume the W displacement at element number E as A0 plus, or we can call it, we can A1 plus A2, A1 plus A2x plus A3x square plus x4 A4x cube. So, our approximation is such that I have 4 unknowns here, A1, A2, A3, A4, they are 4 unknowns, and if the problem is time independent problem, these are just constants, and if they are time dependent problem, then A1, A2, A3, A4 are time dependent, they have time dependent value. So, here I have 4 unknowns A1, A2, A3, A4, and I have the 4 degrees of freedom in the formulation. And the approximation is such that it has at least the second order derivative non-zero, because in the variational form we have seen that the highest order derivative appearing for W is 2. In fact, it has a derivative up to third order also. Now, if this is W, then what we do is we say that at x equal to 0, which means at the first node we have W1e, which is D1e is equal to A1, because at the first node x equal to 0, and then we say at that same node del W by del x 1e is equal to D2e is equal to A2, because if I differentiate it once with respect to x, I get just A2, and the value of that rest of the terms are x terms after doing the derivative, after finding out the derivative. So, these terms vanish, only I am left with A2, and then at x equal to LE I have del 2, which means W2 of E, which means this is D3 of E, and that is equal to A1 plus A2 LE plus A3 plus A3 LE square plus A4 LE cube, and then again I can differentiate this and evaluate at x equal to LE, and that gives us del W by del x at the second node, that is equal to D4E, and that becomes A2 plus 2 A3 LE plus 3 A4 LE square. So, here I have 4 equations 1, 2, 3, 4, and using these 4 equations I can represent A1, A2, A3, A4 in terms of D1, D2, D3, D4. So, let us define this as equation 1, this as equation 2, this as equation 3, this as equation 4, this as equation 5. So, find A1, A2, A3, A4 in terms of D1, D2, D3, D4 using equations 2 to equation 4, and then we put that in equation 1. Then writing equation 1 in terms of D1, D2, D3, D4, we can write that. So, we have found out A1, A2, A3, A4 in terms of D1, D2, D3, D4 from equation 2, 3, 4, 5, and then we put that in equation 1. If I do that, I get the entire expression as W as a function of small x, we have 1 minus 3 x by L e square plus 2 x by L e whole cube, this entire thing multiplied by d 1 e plus we have x multiplied by 1 minus x by L e square, this multiplied by d 2 e, then plus we have 3 multiplied by x by L e whole square minus 2 into x by L e whole cube multiplied by d 3 e, and then plus we have again x multiplied by x by L e square minus x by L e, and this multiplied by d 4 e. Now, this quantity is called, we give a name to it, we denote this as n 1 of x, and this we denote as n 2 of x, this entire thing, and this entire quantity is denoted as n 3 of x, and this one we denote that as n 4 of x. So, finally, again we write W x within each element, within element E as n 1 of x multiplied by d 1, n 2 multiplied by d 2 with of course, the superscripts for element E, d 3 plus n 4 multiplied by d 4, and these n's are called shape functions. So, n 1, n 2, n 3, n 4 are called shape functions. Now, what we do is we put this approximation in the variational form. So, before doing that I need to define del w also. So, we have del w of x, and that is if I take variation here, this n 1 is a known quantity which is defined by us. So, we cannot vary that, whereas d 1 is an unknown quantity. So, it becomes n 1 e multiplied by variation of d 1 plus n 2 e multiplied by variation of d 2 plus n 3 e multiplied by variation of d 3 e plus n 4 e multiplied by variation of d 4 e. Then we put everything in the variational form. So, if I put it in the variational form, the variational form would look like this. So, our entire domain was x equal to 0 to capital L, the length of the beam. However, we have divided the beam into set of elements and total number of elements is n e. So, we should do the integration now piecewise and then add up for all the elements. Now, these shape functions, as we just now derived, they are derived for each and every element separately. So, n1 e, n2 e, n3 4 e, n4 n3 e, n4 e, this means that they are n1 n2 n3 n4 of each element e. So, accordingly the first element would have n11, n21, n31, n41 and so on. So, we need to, as the definitions are confined within each element, we need to do the integration within each element and then add them up. So, for that we write it in this way. We have a summation going from e is equal to 1 to e and then we have n1 e d1 e plus n2 e d2 e So, we have n1 e d1 e double dot plus all the way up to n4 e d4 e double dot. Because we have a term w double dot in the variational form. So, if my w is this, then w double dot is n1 multiplied by d1 double dot, because n1 is not a function of t, but d1 can be a function of t as we discussed. Similarly, n2 into d2 double dot plus n3 into d3 double dot plus n4 into d4 e double dot. So, that is what we are writing here and then we have del w. So, for that we write n1 e multiplied by a variation of d1 e and then all the way up to n4 multiplied by the variation of d4 e and then dx. So, that is the first term, the inertia term, and then we have the next term which gives us E I. Then we have n1 comma x x into E multiplied by d1 e, because if this is my w and in the second term in the variational form we have del 2 w by del x 2. So, if I want to differentiate this, I cannot differentiate d because d is not a function of x. If I differentiate, that will give me 0. So, I have to differentiate n, and after differentiating twice I get n1 comma x x and I get this as this. Similarly, here I have n1 comma x x then multiplied by the variation of d1 and all the way up to n4 comma x x multiplied by variation of d4 dx, and this integral is from 0 to L e, and then we have 0 to L e p z multiplied by just w, and w is n1 e multiplied by del w, and that is n1 e multiplied by delta d1 e till n4 e multiplied by delta d4 e and dx, and that is equal to 0. So, this is the variational form that I get after I put the elemental approximations. Now, again we follow a similar logic. Our variations are all arbitrary Now, the del W is an arbitrary variation and it can be arbitrary only when my del D, del D1E, del 2E, del D2E, del 3E and del 4E are arbitrary. So, del W is arbitrary means the variations of D are also arbitrary. So, what I would do is I would write the entire expression in terms of delta D1 multiplied by few terms plus delta D2 multiplied by few terms and so on. So, if we do that, again it looks like this. So, we have delta D1 multiplied by 0 to LE rho A multiplied by N1 and then we have N1 into D1 plus up to N4E into D4E dx. Similarly, I have again 0 to LE EI multiplied by N1 comma XX and then multiplied by N1 comma XX N1E comma XX multiplied by D1E plus up to N4E comma XX multiplied by D4E dx and then we have 0 to LE PZ multiplied by N1E dx. We keep doing it. So, we do this for delta D2, delta D3 and delta D4. We will just write the last one. So, we write till the last term which is delta D4 and here we have rho A N4E multiplied by N1E D1E plus again N4E D4E dx and then 0 to LE EI we again multiply N1 N1E XX with these terms and then we have here PZ N4E dx and that is equal to 0. So, here we see that we have delta D1, delta D2, delta D3, delta D4 and delta D1 is multiplied with a big expression and so is delta D2, delta D3 and delta D4. Now, the entire summation is 0, but we are saying that delta D1, delta D2, delta D3 and delta D4 are independent variations, arbitrary variations. So, the entire summation can only be 0 when each of the term that they are multiplied with are separately 0, which means this whatever is delta D1 E multiplied with that is 0, whatever is delta D2 is multiplied with that is 0, whatever is delta D3 multiplied with that is 0 and whatever is delta D4 is multiplied with that is 0. So, I get, so each of those terms are 0. So, that gives me 4 equations for each element. So, we get four equations for each element. So, whatever the number of degrees of freedom per element, we get that many equations. In this case we have 4 degrees of freedom, so we get 4 equations for each element and the equations is of the form this K E, that is a 4 by 4 matrix multiplied by D, that is a 4 by 1 vector is equal to F E, that is a 4 by 1 vector and also we have inertia term. So, we will get m multiplied by d double dot E. So, this is a 4 by 1, this is 4 by 4. So, each element gives me a set of coupled ordinary differential equation of size 4. Now, this is called mass matrix, this is called stiffness matrix, this is called force vector. So, this we call mass matrix, this we call stiffness matrix, and this we call force vector. This is elemental, these are all elemental matrices. So, it is elemental mass matrix, elemental stiffness matrix, and this is elemental force vector. So, now that we have defined this for each element, now we have to combine the contributions from all the elements, and then we have to add them up and make a global system of equations which we can solve and get my response of the structure. So, that we will do in the next lecture. I would like to conclude this lecture here. Thank you.